Welcome to the Track Friday Seminar on Transportation. I want to welcome Christine Kendrick here from the City of Portland Bureau of Planning and Sustainability, where she's working on air quality and smart cities. She has a PhD in environmental science from Portland State University, and an undergraduate degree in environmental health science from the University of Georgia. Welcome.
Thank you so much. Thanks for having me here today. As Aaron said, I have a PhD from environmental science, just finishing up this past spring here at Portland State University. And now I'm working at the City of Portland Bureau of Planning and Sustainability, and going to talk to you a little bit about that work today, what we're doing with air quality sensors, and also share a little bit from my dissertation research as well, and how that's kind of evolved into the work we're doing. So I'll start off today with a little bit of kind of background and motivation, go into what we've done over the past 3.5 years, and some initial pilot evaluations. And then I'm going to end today's talk going over kind of our next 10 months, looking ahead, and some current grants that we have that we're working on. So I'm going to start with a quiz. It's multiple choice, so you feel free to answer whatever. But I'm wondering how many of you all know, and some people in this room probably do know already, how many regulatory air quality monitoring stations are located within the City of Portland boundaries? So raise your hand if you think it's A, 6. Okay, a few. B, 4. Okay. C, 2. Okay. And then D, 1. All right. It's actually 1, which is very surprising. Yes. So our one that's actually within the city boundaries is at Southeast Lafayette and 58th Avenue. There are some surrounding Portland, some additional ones in Hillsborough and Vancouver, those blue dots. And then this red dot down here is actually one of our newest air quality monitoring stations. And this is a near-road monitoring station that was the result of an EPA 2010 final rule, which required large population centers to actually add a second near-road monitoring station. And it also lowered and set a 1-hour new standard for nitrogen dioxide exposures. This is a picture of our newest roadside monitoring station. It's located near I-5. And I think across the country, this new rule has resulted in about, I think it's around 150 new monitoring stations that are near roads, which is great. And it's acknowledging the fact that we know from the monitoring research, we see increased exposure concentrations of traffic-related pollution near roadways. This figure is actually a meta-analysis of over 35 different monitoring studies. It's showing increasing distance away from the edge of the road on the x-axis, and on the y-axis, normalized pollutant concentration. So some pollutants have a very rapid decay away from the road, some pollutants a more gradual or less rapid decay. But we see directly in that near-road environment, pollutant concentrations are highest. We also know from the epidemiology and toxicology literature that there's also associated adverse health risks with this increased proximity to traffic. So those new near-road monitoring stations in that network is acknowledging this research. But all of those stations are located near highways. So we don't have any roadside monitoring data on urban arterials or other types of roadways in the roadside environment. So pictured here is a figure of Portland's 20-minute neighborhoods. So we know in Portland we're promoting high density, a mix of land uses, so we know that we're putting some populations in closer proximity to roadways and different air quality sources. But those regulatory air quality monitoring stations are very sparse. It's a high cost of investment, not only money, but also infrastructure. You have to have a large footprint, almost usually a shed, heating and air conditioning for the instrumentation. So what we've been thinking about and working on over the past couple of years, and really ramping up over the last year, City of Portland, is trying to understand how we can harness the power of low-cost air quality sensors. These sensors have a low power consumption and are much more affordable. If we could harness that type of technology, we could greatly increase the spatial extent of our urban air quality monitoring. Our ideas with this increased data is that we would like to make it available not only to our city engineers and our planners, but also the public. Some of the ideas that we could use with this increased data set would be to enable better assessments of public health and equity. We would like to evaluate specific transportation projects. So when we implement a new traffic signal project, such as freight priority signaling or improved transit signal priority, are we actually seeing the mitigation results that we set out to do? Are we actually seeing that change in air quality? And if we had increased data points, maybe we could do some of that evaluation. We'd also like to get better baselines of climate-related variables, temperature, profiles, and CO2. And we can have a better understanding how well we're doing advancing our Portland climate action goals. And last but not least, trying to work on how to make the data open and available to use, possibly integrated with other data sets like traffic and transportation data sets. Can we create opportunities for economic development and civic engagement? So thinking about all of this different motivation and where we want to go with our project goals, we know that roadside environments in urban areas are undersampled. We need improved exposure assessment. I also forgot to mention in my intro, I was also an intern at Portland Bureau of Transportation. And when working there, there was this interest in trying to understand better the connection between traffic and air quality. And again, how can we consider public health in our decision making and our operations? So we thought about all these different pieces, and about 3 years ago, we had an opportunity on Southeast Powell Boulevard. This opportunity was the implementation of the City Coordinated Adaptive Traffic Signal System. So this system, SCATS, dynamically sets traffic signal cycle lengths. It's based on measuring the traffic volumes in the road and along the whole corridor. It's trying to set the timing across the corridor to help move vehicles through and dynamically set the green times and the red times. When this was being installed, we also had the opportunity to combine a couple of different funding sources to actually install a new roadside air quality monitoring station at one of these intersections in the corridor. We did this at Southeast Powell Boulevard and Southeast 26th Avenue. So we used a repurposed traffic signal cabinet, and it's just filled with air quality instruments. So we have a mix of federal reference method instruments. That's kind of our platinum or gold standard of instrumentation. We also have a mix of research grade instruments, so kind of moderately priced. And we installed this, like I said, about 3 years ago. The meteorological instruments are mounted up on the light pole right here. And we've had 24-hour-a-day, 365-day measurements of NO and NO2, PM 2.5, wind speed and wind direction, temperature and relative humidity for about 3 years. And so this work was part of my work at PBOT and my dissertation. And some of the things that we learned from this data set is we performed a seasonal and diurnal characterization on the data. So we don't have a lot of data at the urban roadsides, so what concentrations are we actually seeing? When are they highest? And what we did is we used quantile regression to look at kind of the annual aggregation, so what's the exposure over a whole year, and then also shorter term 15-minute aggregations across different seasons. And the reason we did this is because it's very common in exposure assessment studies to use an annual mean. So that's what we're looking at, longer term exposures. And then they also use traffic volumes as a proxy because it's so difficult to get air quality data. So what we found, showing in this top graph here, is that sure, when we look at it on an annual scale, traffic volumes do a pretty good job of predicting average exposures. So that is a valid method to use when you're looking at longer term chronic exposures. But as we start to want to look at short term exposures, like you're actually experienced as a urban commuter, waiting at the bus, walking to work, traffic volumes are not doing a good job of predicting those exposures, especially in the afternoon and evening. As the atmospheric boundary layer increases, you really see little to no relationship across all seasons for the afternoon and evening. So this kind of tells us that this method of using traffic volumes as a proxy for exposure is not going to work as we try to improve our exposure assessment and look at different urban microscale exposures. Another piece that we did with the initial roadside air quality monitoring data set is we actually took advantage of some natural experiments that occurred with changes in the traffic signal settings. So pictured here is actually the diurnal cycle length pattern. So 0 to 24 hours, and this is the cycle length on the y-axis. So the gray periods are kind of our background periods, and then there was an issue of pedestrian delay. So it was taking too long for pedestrians to cross. So they wanted to experiment with lowering the cycle length and then seeing what happened in travel times and air quality. And so the black dots are showing the treatment period where they lowered the cycle length. So there was 2 case studies like this where we were able to gather the air quality data while they made these changes and manipulations to the traffic signal, and we actually did demonstrate that the reduction in that maximum cycle length resulted in an increase in NO and NO2. So they have to think about these trade-offs and using air quality as a performance metric. If it still is better to get pedestrians across, then we'll go with that decision, but here's another piece of information that we can use with this air quality data set. Now, this was not a simple comparison to make because we only have one site. We don't have a set of a control site and our treatment site. So we actually had to use time periods as our control and treatment periods, which is very difficult because the week before the cycle length is reduced, the weather is very different compared to the week where you actually reduce the cycle length. So we pulled a method called propensity score matching and match sampling from human health studies that have a lot of natural variability. You can't really control for all of the different factors. And so match sampling is a way to actually control for the different variables and help compare apples to apples. And this is the first time that this type of method has been used on a time series data set. And so this is really exciting that it worked. We showed that it could work, and that this is something we would have to use in future evaluations, even with the low-cost sensor data as well. So we had a lot of success with the first station. So over the past year and a half, we've invested and built a second clear cabinet. This is located out on 122nd and Division. It's housed again in a traffic signal cabinet, a little bit larger. We have a lot more space. So we added an additional instrument in there for black carbon measurements. So we'll actually be able to see the specific impact from diesel vehicles. We also had to be a little bit more creative with our sampling inlets because it's not on the traffic pole. We kind of hid the sampling inlet like this on the pole in the first station, but this is very much out in the open. And so we kind of designed this little mesh cage to protect the sampling inlet so folks can't try to throw stuff up inside the cabinet. We also, kind of lessons learned, had a better mounting of our meteorological equipment. When you install wind sensors, you really want to make sure there's not anything around them. So this is really exciting to have a little bit improved wind data as well by installing it on the traffic signal mast arm. But this might look familiar to you all if anybody has seen the Portland's U.S. Department of Transportation Smart City Challenge proposal. And as we start to think about the future, again, we want to start to look at these test corridors and these living laboratories. And so the orange dots are potential air quality sensor locations. But we can't build a clear station on every single corner. It's a lot of investment. It's a lot of power. Doesn't really make sense to make that kind of investment, even though we know it worked. So the idea to be able to extend out our air quality measurements is to locate low-cost sensors around those clear stations. But we also know, unfortunately, the state of technology with low-cost air quality sensors isn't quite there yet. A lot of the initial devices that were proposed to us had the first level of problem, which was minimum detection limit versus ambient concentrations. A lot of the sensors that are available out there in some really cool do-it-yourself kits, they're $8 to $10. Sounds really exciting, but the minimum detection limits are magnitudes higher than what the concentrations we actually see in the ambient environment. So this is an example. The red line on this graph is showing the minimum detection limit for, I think there's 3 different sensors there that are often used in some of these air quality eggs or different types of devices that are make yourself or kind of the first draft that people usually try to make with sensors. And that minimum detection limit is above 95% of the concentrations that we actually see in the urban background and at the roadside, even where pollution's elevated. So it's kind of the first hurdle. You have to be able to find sensors that can actually have the range of detection that we see in the urban environment. We know that these sensors also have interferences with temperature and relative humidity. It's just electrical signal. So when temperature changes, you can start to measuring that as long as you're also measuring the gas that you're interested in. Additionally, they have cross sensitivities with other gaseous pollutants, and trying to understand what are the actual solar panel capabilities with these sensors, if they are low powered and they're in Portland, where we don't have sun throughout the whole year. So what we did, starting in, I think this is about fall of 2015, we did a small pilot evaluation and worked with one device called the AirSense Pro. And kind of through discussions, upgraded this device to have electrochemical sensors. So instead of those $10 sensors, they're about 200 or 250 a piece, but they have that minimum detection limit. And as an air quality scientist, $250 for a sensor is still very low cost compared to a $20,000 instrument for one gas. So what we decided to do is first do a co-location study at the DEQ monitoring station at Southeast Lafayette and 58th. That was that first one dot that's within the city of Portland boundaries. And by co-locating there, we could actually look at the comparison between the sensor measurements and our reference instruments. And we co-located 3 of the sensor devices because we also wanted to understand how well the sensors are telling the same story as well. So here's some of our results. Unfortunately, we learned a lot about data recovery and some issues with cell phone service and cell phone modems. So pretty poor data recovery, but and even though this is a negative result, was still a lot of lessons learned about how to better wire things, different devices that you can choose to send the data out. The sensor temperature was always biased high compared to the DEQ reference measurement. Again, really great lessons learned. The way that the box was designed, we were pretty much just measuring the internal temperature of the box and the electronics, so it's always going to be biased high. So how can we better think about how the box is configured to get a better actual measurement of ambient temperature? And it's also not bad to have the internal measurement of the device as well. It can help give us some specs for how well the board is doing. The NO2 data was not super positive as well. Lots of outliers and negative values. You can see right here the range of the sensor concentration, which is on the y-axis, is for some of these sensors is from -200 to 300 ppb, while our reference instrument is going from 0 to 35 ppb. So obviously some mixed match. What's happening? Why is there such a large range in the outliers? And then if you actually zoom in on the actual ambient range of concentrations, we see we have a huge resolution issue. If these data points are jumping 10 ppb or 5 ppb, that's not enough resolution that we actually need to measure, again, the ambient urban environment. For the PM data, we really saw no relationship with the DEQ measurements, and we saw kind of a bimodal count. Most of the data was either 500 or 0, which again can tell us about some of the electronics issues with how the sensor was put together, and also sampling inlet. These particle counters are usually just using a little laser or a light. So it's going to be very sensitive to how you're actually pulling air in. It's going to be sensitive to relative humidity as well. The CO actually showed some promising results, which is common with the literature, that CO is kind of the most successful low-cost pollutant that you can measure with low-cost sensors. And so you start to see with this, you see a little bit of 2 different relationships happening with the sensor versus the reference instrument, and that is actually because of interferences issues with ozone and NOx. So right here, there's different concentrations of ozone that are occurring, that are making this pattern different than right here with ozone concentrations. But those are things that we can model. If they're consistently different, we can actually adjust the data back, and we know these are known interferences. So summarizing our pilot, we kind of knew about these 2 first issues, interferences with temperature, relative humidity, cross-sensitivities with gases, and we did see these issues. But these are things that, as we get better testing and more data, we can figure out, again, what's the right quality control algorithm and protocol to adjust the data back to the reference instruments. And then we also had some new issues that were highlighted by the pilot. Data recovery, electronics interferences with the signals, and resolution. And we really need to think about sampling inlet design. Even though most of these sensors are passive, so they're not having a pump pull air in, we still have to think about how the air is getting to the samplers. So, coming from our pilot evaluation, we started talking to a lot of the different research groups that are working around the country on this and different laboratories. And we decided to write a proposal for the NIST Replicable Smart City Technologies Cooperative Agreement Grant. And we were successful in getting this. We found out in August we've got this grant. And what we did with this grant and what our goals are over the next 10 months, it started in September, so we're about 2 months in. We are going to have more co-located sensor evaluation deployments. We are also working to develop standards for the sensor air quality data. And this is both for data formats, how's the data coming off, how's it fed into our data management system. Those standards are really important for working across cities and if we want to make the data open to different APIs and whatnot, but also standards for the data quality. So what are those QC procedures that other cities need to look at to make sure and adjust the data when you have those interferences? And then our last goal with this project is to kind of take lessons learned throughout the whole year and develop specialized guidelines for other cities on how to use and deploy low-cost air quality networks. And what are the different criteria, considerations that need to be met to improve data quality? So at the same time, over this next year, Portland State researchers, Kristen Tufte, Linda George, and Dave Meyer, got an NSF EAGER grant. And it's very complementary to what we're doing with the NIST grant. So we're very excited to run these projects kind of side by side over the next year. And with this EAGER grant, they're going to expand the sensor deployment from into the neighborhood around the roadway so we can start to ask some spatial density research questions. There's also going to be a little bit more incorporation of low, moderate, and high cost sensors. So can we help improve data quality by kind of having a scaffolding of sensor quality? And then it is a grant in the computer science division of NSF, so a large piece of this is developing agile data integration management system, a system that can handle the quantity of data that's going to come off of these sensors and also deal with the data quality issue that's going to happen with these sensors. So over the past month and a half or 2 months of our NIST grant, what we've primarily been working on is a very thorough, large sensor review. Since we've been doing this work, we've been approached by lots of different companies, vendors, startups who have different air quality sensor devices. So what we did is we took a look through all of the different companies that we knew were out there, and we reviewed them based on certain criteria that we set in order to meet our project goals that were at that very beginning. We want to evaluate transportation projects, climate change goals. So what do we need in a sensor that can actually meet those larger long-term goals? Some examples of that criteria are, does the sensor have any pre-existing evaluation data? Has the sensor vendor or creator performed any extra calibrations? And another example is the sensor device ready to be deployed outside. City of Portland does not want to be in the business of building weatherproof housing and building our own housing for these devices, so we need something that's ready to go, ready to be deployed outside. So based on our review, we decided to move forward with a multi-vendor deployment. We were originally thinking we would do a pilot study of 10 sensors of all the same, but from this review, we identified these 3 groups that have different pros to them, and so we think it's useful to do the multi-vendor. NIST is also very excited about us doing a multi-vendor deployment because it can help answer that more complicated question about standards across different devices and vendors. So we're in discussions with Argonne National Laboratory and to use their Waggle Array of Things unit. This unit has been developed from another National Science Foundation project that's been developed over the past 1.5 years, and they're deploying 500 of these sensors across Chicago. So Portland is going to be a pilot city for some of these sensor devices. We're also working with Sensevere, a company from Pittsburgh, who has been working with Carnegie Mellon universities in the Atmospheric Particle Center. And they have about 20 units deployed in Pittsburgh right now. They've done a lot of calibration studies and work over the past 1.5 years. And they're excited to try and deploy the device in a very different climate than Pittsburgh and see what happens with all this rain over the winter. And then last, another device that we are in discussions with is from a company called Apis. And that is pictured here. Oops, let me go back. Really looks like a nice speaker. And they are actually currently already doing a co-location study at the Oregon DEQ station right now. And this company was started up by folks that have been in the air quality monitoring instrumentation business for quite a while. And they actually built a pump to pull air in their device. They have a nice cooling mechanism to cool down from the electronics. So a lot of design has gone into this device. So we're excited to take a look at that one as well. Another piece of the work that we're currently doing is working with the Green Electronics Council to develop a first draft of some guidelines of how to improve our ability to recycle Internet of Things electronics. Right now we're doing a deployment of about 9 devices, but the long-term goal is to put these devices across the whole spatial extent of Portland, and that's going to start increasing and snowballing the amount of electronics that are out there. Many other cities are talking about the same thing. So is there something we can do right now before things start growing quicker to help minimize our electronics waste and maximize the ability to repurpose or reuse these sensors? They stop working in the roadside environment. Is there a secondary market for these sensors as well? So we're excited to work with Green Electronics Council on creating these guidelines. Upcoming, once we get the sensor devices, again, we're going to start slow and do another co-location study at the DEQ station. This is the top deck of the station, so there's lots of room on the railing to mount all these sensors. AC power is accessible, so as soon as we get the sensors, we can plug them in and start to see what the data is saying. Again, we want to start to understand what the sensors versus the reference instruments relationships are, and also sensor versus sensor. Are there any adjustments we need to make so we get all 3 of those waggle array of thing units as close as possible telling the same story before we spread them out and put them out on the roadside? After this co-location, we're going to move out to the roadside, and we will deploy these out in the roadway corridor. We will place them near our clear cabinets because, again, this is another good check that we have of reference instruments. We might need to calibrate and adjust the data, so we want to have this other kind of, I keep saying, but it's a clock to kind of tell what the right time is or what the right concentration is. This deployment will be longer term, 4 to 5 months minimum. We hope longer if we can kind of keep things moving quickly. With this deployment, we want to start to understand what's the drift over time in these sensors. Any air quality instrument requires a lot of calibration and has natural drift, and so these sensors are no different. So how quickly does it drift? How can we adjust the data back? Are there any effects of putting the sensors in a high pollution environment? Sometimes these sensors can burn out quicker if they have a lot of peaks and spikes. And as part of that, we really want to document what is the maintenance that's required for these sensors. Can we really just put them up and forget about them? Are we going to have to get the bucket truck out there and going out every 2 months, every 1 month? And we want to estimate what those costs are. And that's information that's going to be really important to deliver to other cities looking to do this type of deployment and build this network. So maintenance, along with a lot of the calibration and data quality issues, are things that we're going to compose throughout the project to create guidelines and create this framework for using low-cost sensors for urban air quality monitoring. The idea behind that is, again, we want to have these systems be interoperable across cities. We want to be able to share data. If Seattle has some sensors going up, how can we make comparisons across that? And so developing, again, those protocols for data standards are going to be really important over the next year. We hope to publish some papers documenting our results. There's really a lack of evaluation studies in the atmospheric science and physics literature. So with this data set, I think we have a lot of different research questions we can explore. And it's also interesting, this NIST grant is a cooperative agreement, and so they wanted to write papers with us. So it's kind of a unique grant. We're on the phone with them. We have bi-weekly phone calls with NIST. So that's another big push over this next year. And another idea behind this is, this project is very much focused on air quality sensors, but it's also just, in general, an Internet of Things pilot. How easy it is to deploy sensors outside. How are we doing communicating the data back to a central place? How well are we sharing that data across bureaus or across the city and the university, the city and the public? So there's a lot of things that we're kind of ideas that we're testing out through this pilot. And if things go well, can we think about this future sensor network? If we can create this environmental data layer for the city of Portland, that'd be really exciting. There are things we can add, water quality sensors and stormwater management. So there's a lot of ideas out there that we want to explore coming up in the future. And even specifically with this pilot, we're also working on our open data policy, community engagement, which is also communicating the data to the public, but also maybe there's some public engagement in selecting the sites of where we put these sensors. How can we kind of do that and create some models off of that? I think we also, in terms of air quality data, need to think about how to communicate the data we're getting off of air quality sensors. These might be 5-minute short-term concentrations. What does that concentration mean in terms of this National Ambient Air Quality Standard and criteria pollutant that I see on these other maps, the EPA regulations versus the data that we're getting? So those are some big questions that still need to be wrestled out. You know, sometimes when I'm out at the site, I see a dump truck go by, very, very large peak of NO, 134 ppb. The next minute, I still have 150 ppb of NO2. That's an extremely large value. But it's there for about a minute and a half. So what does that mean in terms of kind of your hour commute exposure, your long-term exposure? A lot of things we need to figure out with communicating this new type of data. So I think with that, I'm all finished up. I just wanted to thank my team at Portland State University and City of Portland, a lot of great interdisciplinary folks on these projects. And then, of course, acknowledge the funding over the past few years through my dissertation and then also the City of Portland work. And there's my email. Please feel free to email with any questions, and I think we have plenty of time for questions right now. Yeah.
You said that one of the issues with the sensors you were having was how to get the air into the sensors?
Yes.
Did you guys ever try putting any kind of swivel and a wind vane on it so that way the intake is always facing the wind?
Yeah, and that is a great idea. We were not actually the City of Portland designing the sensor device. We were working with a consultant who was designing the device. But those are great things to think about for the next iterations. And kind of after we did that pilot, looking to other groups that were doing that research, I think there's a lot of unique ideas. I haven't seen that one yet, but I think that would be really neat. We don't tend, in air quality monitoring, to necessarily move the inlet facing. It's kind of usually just facing down. We want to make sure there's lots of air around it to go up. But maybe you do need that type of design with these passive samplers to help get more airflow to it.
I'm interested in some of the sort of the policy implications if we were able to get more of this sort of granular, accurate data about, in terms of like what it means for transportation planning in Portland and land use planning. And I'm curious, I saw Peter Kuntz's name up there. I've worked with him a little bit. What sort of ideas does he have, or does PBON have, that's sort of driving this?
Yeah. I think one of the main drivers behind this, and really our first idea of the application that we would use with this data, is a little bit more small scale, and that's evaluating transportation projects. It's kind of what we did with the first roadside station. We made those changes to traffic signals, and we saw that increase in NOx. So kind of using that same model and some of the same techniques, if we're doing this new project over here, we're actually investing in freight priority signaling. One of the goals of that is to actually mitigate emissions. So are we actually meeting those goals? So that's kind of the first use case, and that's small scale and project by project, using it to evaluate. Now, as you imagine, if we have a network of sensors, there's a lot of other spatial and research questions that we can do with it. And so I think that's kind of what we have to think about, how you're communicating the data, what it is useful for, and a lot of cities are going to have to grapple with this as well. And data quality is going to be huge to that. What's the actual range of variance in the data quality that we can actually make a decision on the data as well?
My name is Matt. I actually worked for a company in Utah that deploys Bluetooth and Wi-Fi sensors to measure traffic volumes. So I'm interested in what technology the SCATS system uses to measure traffic volumes.
It's loop detectors. So the loops right at the stop line.
Does have Bluetooth detectors on the same corridor. It's not feeding the SCAT system, but it's for other data collection purposes.
Yeah, I think in Portal you can see all the places that the Bluetooth readers are there to get travel times. And so that was actually when we did the comparison of reducing the cycle length. We were looking at the trade-offs in air quality. We also looked at the trade-offs in travel time. And for that data, we used the Bluetooth readers and not the loop detectors in the SCAT system. Yeah.
Thank you.
Hi, Becca Bryce. I was curious about more like the biker commuter, because I know that the city of Portland has a large biking community, and I know that also Portland State Transportation, I know that they've done some smog or tried to find out the emissions for the biker community. I was wondering, like, weren't you just saying for a 15-minute commute? I was wondering if you would think about, like, maybe the average bike commute and
Absolutely. And for that, I think you really want to get to the exposure piece. Right now, I'm kind of talking about exposure concentration, which are just straight the pollutants that were measured. We start to think about bicyclers, even if they're on lower traffic streets, if you did take her out of that, your pollutant concentrations are higher, you're breathing in a lot more. So you really need to get to that exposure piece. And that's kind of another idea with going back to your policy question and thinking long term. If you actually did have a network of sensors, you could start to model that and map that. And maybe even you just focus on a few major bike routes, a few major corridors, then can you build a predictive model for other types of routes instead of putting a sensor, even the low-cost ones, at every single intersection? Those are great questions that I think would be great if this data set could eventually get there.
I should introduce myself if I'm going to keep interjecting in some of these comments, but I'm going to talk to the group for just a quick second. My name is Adrian Piermine. I'm with the transportation consulting firm DKS Associates, and I'm their national director for smart cities and connected vehicles. And Christine and I are on we've over the years built a consortium of partner agencies, different departments in PSU, different departments in the city of Portland, the Technology Association of Oregon, Intel, the whole big consortium of public-private institutional partners that we're now calling the Smart Cities Lab. And one of the things I really want to encourage in here is any of these types of research projects that sound like they're of interest to you, that combine smart cities issues between data collection around air quality and transportation or water transportation, all kinds of different things that aren't normally correlated in just one of those disciplines. We have access to this group that can help make connections within the different city departments and make connections with other partners like Intel and other technology vendors, and would be really happy to help encourage any of that sort of research, because we're really setting the region up as nationally recognized. I don't know if everybody, when you mentioned NIST quite a few times, the National Institute of Standards and Technology is really looking to develop more standards around Internet of Things and smart city solutions. So lots of great research ideas. Part of the reason that we chose Powell Corridor as the pilot was to eventually, over time, continue to build it out as not just Powell, but Powell-Division and Clinton in between. And so there's kind of a microcosm of all things city, from a big high-throughput roadway like Powell-Division, more inner, dense infilling, and then the major bike path along Clinton. So it's got the potential for all kinds of interesting urban research, we think, over time.
Also, now, really, we're moving our focus out to 122nd Avenue in East Portland, which are increasing bus routes out there, and the bike routes. There are some major bike routes on there. So how does that look for pedestrians and bicycles in that environment as well?
Why not focus down here, downtown, where there's more stop and go traffic, where there'd be more pollutants output from cars?
Well, that's a great question. There is still quite a bit of stop-and-go traffic, at least at rush hour periods. This is a little bit more constant throughout the day. The roads might be a little bit more full. But we also, having those clear cabinets and those reference stations out on Powell and Division are really great for the test beds. So let's kind of focus the research there. Again, it'd be great to put clear cabinets everywhere. We could ask a lot more questions, but yeah.
My name's Scott. I'm curious about the NIST grant. You said they were working with you to write papers and stuff. Is that I'm curious why? What
Yeah, it's a very unique federal grant. So we really don't necessarily see this with NSF or EPA grants, but this type of grant they're calling a cooperative agreement. And it's exciting because they want to offer the assistance of all of the National Institute of Standards and Technologies. Thank you, Adrian, for reminding me. NIST scientists. They have a lot of different groups: greenhouse gas groups, smart grid, electricity groups. So there's a lot of scientists there, and they kind of want to understand how they can help us and work on that together. So it's a really exciting opportunity and very new. So we'll see how it goes over the next year. It's really helpful. You have biweekly phone calls. You're making progress every 2 weeks when talking to them. But co-authoring papers on them will be something new.
To that. So NIST is a department that's kind of almost directly under the White House through the Department of Commerce. And the White House has had a number of initiatives that they're trying to put out to stimulate the smart cities and Internet of Things economy and get more and more of these devices and prove the concepts. But there's very little standardization around the quality of the types of data that you're trying to collect with any of these different smart cities technologies. And so if you, rather than just waste federal money by buying a bunch of cheap, crappy products that aren't actually collecting the kind of data we need, they want this kind of research, and then they want to use that research to set standards. So that's kind of the underlying motivation.
This is really trying to accelerate the best management practices that come out of this research and kind of help. They don't want to like lay down the law and say this is the standard that they're used, but they want to pay attention and then accelerate kind of what works best to help move it forward.
So with your calibrations, especially against existing sensors, I know that quite often internal clocks get off a little bit. So how do you know that you're actually measuring something different as opposed to, as you said, a diesel truck went by, so it's at 1,000 for one sensor and at 10 for another that was measured just before the truck came by?
Yeah, well, and that's difficult, and that's why a lot of these, even the more expensive air quality instrumentation, you have to calibrate often because, even clocks can drift. Same with these values and the baselines and the calibration curves. So that's why kind of DEQ is that platinum level of standard. They have to follow federal protocols and how often to calibrate, how to check things. And so that's kind of the best you can do is make sure you're calibrating your reference instruments with known gases at known times, and then we're going to use that data to adjust the sensor data back.
But then you were also showing your graphs together, and so you were saying that some of these weren't as good. Could that possibly just be because there's more natural variability within the 5 minutes and they were testing 10, 15 seconds apart?
With the lower cost sensors? It could be. I think that's kind of why we started at the DEQ station, is that there isn't as much variability, so it's not right outside the road. It's kind of a block in, so it's a little bit more stable, and that's kind of why that station is there. It's supposed to get an average urban background concentration. So that's kind of the purpose of starting there, is to not have that intense flux and change. We will still have to tackle that when we get to the roadside, but yeah, so we're kind of starting there. What do the relationships look like? And then we'll go and see how we work with the fluxes. Good question, yeah. Thanks.
Hi, I'm Gloria, and Gloria Pinzo. And I was really curious to find out, I know right now you're kind of limited to kind of using the existing locations where you could put, but once you start moving forward, how are you using any like health data about, maybe asthma or things like that? Like how are you using that to influence where you put these sensors?
That's a great question. I think that component, health data, and a little bit more social engagement of where folks are interested in or it would be valuable to the community to put sensors is something we really want to incorporate as we move forward and to create that network. Right now, we're focused on the transportation corridors because our research projects are transportation focused. So we're going to go where we're either have the ability to change signals or do those projects. But looking ahead and for other use cases, public health, equity assessments, we don't want to look just at those roads where we have traffic data. So, great question.
I have another question. I was curious about so you mentioned the community engagement. I was wondering about your ideas about how to get the data to the community, how you're going to present it to the community.
Yeah, that's really new, and we're still working on it. So right now, the first step is building our data management system to get it all into one place. We're working with the multi-vendors, so it's kind of going out to the different vendors, we have to pull it back in, and then how are we first sharing that across the university and bureaus? And then it's trying to figure out how to make an open layer to the public as well. So those are things we're still completely in development phase.
So I've got a bunch of questions from our online viewers.
Oh, okay, great.
So do you want me to just give them all to you and then you can piece through them? Or?
Let's do one at a time so I make sure I remember all of them.
Well, the first one is related to some other questions, but are you also going to be monitoring away from the corridors to see the effect of the corridors on residential areas?
Yeah, I mean, as an air quality scientist, that's a question that's really intriguing to me, understanding what the decay away is. Are there other sources? What happens when you have two major roads and that neighborhood's in between? Does it actually decay back down to background concentrations? And that's what's exciting about the NSF EAGER grant that the Portland State University research got, because now we can expand how many sensors we can actually deploy. they'll use a little bit different type of sensors, but that's the idea, is to put it into neighborhoods and kind of start to understand that gradient.
Next question is there a private sector interest in some of these questions and sensor networks?
Yes, absolutely. I mean, two of the vendors we're going with are private companies. They're looking to figure out how to build this model. They're startups. So right now it's still kind of prototype phases, research and development. That's why it's kind of nice to be able to work together on figuring out some of these research questions. And we can save some costs as well. So yes, folks are looking to figure out how to make this a profitable model for creating air quality sensor networks.
Another question is, what about at higher elevations? You have other kind of pollutants. You're kind of measuring heavy things that are street level.
Yeah, we haven't thought about doing different heights. I think for that, I would kind of, for right now, for the grants and our project focus, we want to get as close to breathing height as possible because we're curious about exposure for urban residents. Now, if I was writing a new NSF proposal and you wanted to start to look at climate and regional models, you might want to get a little bit more different heights. So you're trying to understand different questions on that side. So not right now in the work, we aren't.
There's a question that's more about networking protocols like Zigbee, and if you're considering that can handle hundreds of devices.
I haven't specifically heard of Zigbee. So there's a lot of different kind of platforms, networks out there, and that's a difficult piece to sift through. Because again, like the private piece, that folks are trying to figure out how to make it a business as well. And so I was just actually in DC all week for a NIST GCTC, which is the Global Cities Team Challenge kickoff event. And I had a meeting just yesterday with all the other RSCT grantees. And Montgomery County, Maryland is actually doing research on that and doing a nice evaluation of different platforms, what kind of protocols are good for certain. Like if you're doing remote sensors and you don't need to send the data up often, maybe this type of platform is better versus if you are doing an urban air quality measurement and we want to send a concentration every 5, 10, 15 minutes. So we are going to work together with them and kind of see where pieces overlap. They want to add air quality sensors to the dashboard and all the protocol testing that they're doing. So we'll kind of see how that goes and try to learn from them.
Last question that I have here is, how do you test the equipment initially? Is it against a known gas? I mean, how is it calibrated initially?
Yes. Yes, so we are known gas, so you actually have, you test it with a known zero. So you have run a bunch of filters on the air, so we are pretty confident that we're getting actually zero. There should be 0 NOx in there, or 0 CO, or 0 ozone. Put different filters on it, kind of get your first point, and then you're running it at different known concentrations of the gas, creating a calibration curve. So that's how we calibrate each instrument. Sometimes we can do that out in the field when I bring a tank of gas out there, but most likely we're bringing it out to DEQ's labs out in Hillsborough, where they have that facility to test.
I'm Jaime. Do you think that you are going to be able to get like guidelines for optimization of networks, traffic networks, after that?
Not necessarily with this project. There's a lot of folks that study just that, just adaptive traffic signal systems, just optimization and modeling. And so if that, we kind of found some smaller relationships that fed into those models, that could be helpful, but we're not primarily doing that with this project. But that would be the ideal. But how do you also minimize? Are you minimizing or optimizing it for traffic flow? Are you optimizing it for pedestrian safety, for lowering exposure? So you still have to think about those trade-offs in that kind of project. Okay, any more questions? All right, great, thank you so much.